So when we're trying to simplify our radicals to simplest form, a couple of major things that we always want to do. So the radicand of an nth root, we always want to be as small as possible. So if we do a quick example here, if we take a really basic one, if we take rad 8, right? This is one that we should all be really comfortable with breaking down. We'd say, all right, that jumps right to 2 rad 2, right? Rad 4 times rad 2, rad 4 becomes a 2. That's something that everybody should have no problem with. So the root index on the outside, we also want that as small as possible. So taking an example, if we start with a little bit of a bigger root, if we say something like 4th root of 64, a couple different ways you could go at this. You're usually trying to figure out what the smallest base on these would be. So if we broke that down with 64, especially if you're using your exponent table, you could say, all right, that's equivalent to saying 4th root of, it would be what? It would be 2 to the 6th power, right? If you wrote that as a fraction, or if we wrote the exponent as a fraction, we'd say 2 to the 6 fourths. So we got 2 to the 3 halves, right? So now if we rewrote that back in radical form, that 2 is the root index of 2 to the 3rd, so square root of 8, which we just did previously, so that gets us right back to 2 rad 2. So in this case, we not only simplified the root index, we also made the radicand smaller as well. Last thing that we look for, we want no radicals in the denominator, and we also want, say, no fractions under the radical. All right, so 2 big rules, both of which you should be pretty familiar with at this time. All right, let's try a couple practice ones out. So we got square root of 243. Everyone should be familiar with this, but if there's no number on the outside where the root index would be, we are assuming that that's a 2. It's the square root when there's nothing there. So if we're breaking down 243, we're looking for the largest perfect squares that go into that. So if you kind of take a second to think about it, this would be what? We'd break it up, square root of 81 times square root of 3. Always writing that perfect square on the outside first, because then we take the square root of 81, we've got 9 rad 3. Can't simplify the rad 3 anymore. That's our simplest form right there. For the second one, we got now the cube root of 128. So I'm going to talk about 2 different ways that we could solve this. And then going forward, you can kind of pick whichever way makes the most sense to you. And you'll see that we're going to get down to the same end result. So with this, we're no longer looking for perfect squares that go into this. We're looking for perfect cubes that go into 128. So if you're thinking about your perfect cubes, the largest one would be cube root of 64 times cube root of 2. All right, so cube root of 64 is just 4. So we got 4 times cube root of 2. And that is our simplest form. So with this particular one, I think that's the easiest way. I'm going to say or, just to talk about a different way that you could go about it, kind of like we did earlier. So if we have cube root of 128, if we wanted to write that with as small a base as possible. So above we had 64, we rewrote that as 2 to the 6th. That means that 128 is going to be the same as 2 to the 7th power. So now if we write that in exponential form, this is like saying 2 to the 7/3. Right? If we break that up, this is kind of like saying 2 to the 6/3 times 2 to the 1/3. Right? So we got 2 squared times 2 to the 1/3. And then if we just kind of clean that up a little bit, we have 4 times the cube root of 2. As you can see, obviously we got the same exact answer on both. On this particular one, the first one seemed a lot simpler. On some of the later ones, breaking it down with that smallest possible base, I think, will be pretty helpful. All right. I would say maybe pause the video for a second and everybody try number 3 out. Number 3 is something that I think you guys should all be able to do on your own. So maybe pause the video for a second and then try this one out, and then you can check your work in a second. All right. So now if you're checking your work, hopefully when we broke this all down, we said rad 64 times rad 2 for our first part, plus rad 9 times rad 2, plus rad 64 times rad 3, and then now we're in cube root, so minus it would be cube root of 8 times cube root of 2. Simplify all of this, and we've got what? We've got 8 rad 2 plus 3 rad 2 plus 8 rad 3 minus 2 times the cube root of 2. All right, now we need to combine some like terms. So when you're combining like terms with radicals, the rule is you can only combine things that have the same exact radicand. So the number underneath the radical has to be exactly the same, and then you just add or subtract the numbers out in front. So 8 rad 2 plus 3 rad 2 is going to become 11 rad 2. The 8 rad 3, there's nothing we can do with that, and then minus 2 times the cube root of 2. So our final answer is going to be all of that right there. All right, moving on to a couple more challenging ones. We got the 8th root of 64. So these are ones where I would strongly suggest to just try and break down the number underneath the radical into the smallest bases possible. So if you have 64, we've seen this one before, that's 2 to the 6th. That 8th root is the same as saying to the 1/8. So if I rewrite this as 2 to the 6th to the 1/8, I personally think that getting everything into exponential form makes it much easier to simplify, and then you can just rewrite it back into radical form at the end. So we have 2 to the 6/8. So remember your exponent rules. When a power is raised to a power, you're multiplying there. So 2 to the 6/8, which we can say is 2 to the 3/4. Right? So that's the 4th root of 2 to the 3rd, right? Which is just going to simplify to the 4th root of 8. So we broke down, we simplified that root index. We got our radicand to be smaller, all things that we're looking to do when we're simplifying these. If we think about 216, we can rewrite as what? That's going to be 6 to the 3rd. So we have 6 to the 3rd to the 1/6. So we can simplify that as just 6 to the 1/2, which is just going to become rad 6. So not too bad there. All right, with the 6th root of 72. So when you're thinking about numbers that go into 72, obviously you've got more factors here. So you got more options. We've got, I don't know, whatever comes to your head first, you can kind of think about. So I'm thinking 8 and 9. So we'll kind of look at 2 different ways that we could do this, and then we'll talk about maybe why they're different, which would be a better solution, what's more simplified. So if we have 8 and 9, I've got 6th root of 8 times 6th root of 9. If I break those both down to have the smallest base as possible, this is the 8, I can say is 2 to the 3rd. Then that 6th root, I'm just going to rewrite that as to the 1/6. And then we have 3 squared to the 1/6 with the 9. So when we simplify this, we've got 2 to the 1/2 times 3 to the 1/3 that'll become. So we got rad 2 times cube root of 3. Right? So pretty simplified. Everything's broken down pretty good. So another way of looking at it, if the first thing that came to mind for you was, let's say, 36 and 2. So we got 6th root of 36 times 6th root of 2. If we keep going with that, the 6 squared, so 6 to the 2/6. We've got 6 to the 1/3 times the 6th root of 2. So as far as we can go with this one, we've got cube root of 6 times 6th root of 2. If you're comparing these two answers that we got there, right, I think the square root of 2 times the cube root of 3, we've got smaller root index, we've got smaller numbers underneath the radical. That's definitely a more simplified form. So the goal on these, the things that you're looking for, you're always just trying to get, in my opinion, the smallest base number as possible with them. All right, moving on to a couple of different cases here. So some other things that we said to avoid. We said we didn't want radicals in our denominator. We didn't want fractions underneath our radicals. So we're seeing both of that with example 7 and 8 here. One rule that hopefully you guys remember from earlier, if you had square root of A divided by square root of B, this is equivalent to saying square root of A over B as long as the root index is the same for both of these. So we're going to kind of go in both directions with these. So I'd always say when you have a fraction divided by a fraction, look and see if you did put them together, would you be able to simplify the numbers? So 12 rad 2 divided by rad 6, the rad 2 and rad 6, we could simplify to just being a rad 3 in the denominator. So this is equivalent to saying 12 divided by rad 3. Right? From here, we're saying we need to rationalize the denominator. So the way to get that denominator rationalized, we're multiplying by rad 3 over rad 3. Right? That's going to take us back to 12 rad 3 over 3. Always looking to continue to simplify. The 12 and the 3, we can simplify to 4 rad 3. You would have gotten to that if you just multiplied by rad 6 over rad 6 right from the beginning and then simplified. It would have been a little bit more challenging of simplifying, but obviously the numbers are really small either way. It's not going to be something that's too difficult for any of us. That being said, if the numbers were larger, if it was more difficult to simplify, it would make sense to simplify the 2 and the 6 at the beginning rather than at the end. All right, so moving on to number 8 with cube root of 1/2. This is something, the 1/2, we can't simplify anything there. So this is one where you need to break it back apart. So we're actually going kind of in the opposite direction if we look back at what we have at the top of the page there. So this is the same as saying cube root of 1 over cube root of 2. Right, cube root of 1, we all know just to be 1. So now 1 over cube root of 2. This is where this gets a little bit tricky because we can't just multiply by cube root of 2 over the cube root of 2. If we did that, we would end up with the cube root of 4, and 4 is not a perfect cube. So the first instinct is just to rationalize that, multiply by the number, but you need to focus on whatever that root index is on the outside. We need to get to a perfect cube. So when we're thinking of what to multiply this by, we need to think about what our perfect cubes are. So we need to get to, in this case, we want to get to an 8. So what we need to multiply by is cube root of 4 over the cube root of 4. So if that doesn't make sense, hopefully in 1 second it will. So when we simplify this, we have cube root of 4 divided by cube root of 8. So instead of multiplying by the 2, we multiply by 4. That got us to 8. Cube root of 8 we can simplify to just a 2. So we have the cube root of 4 all over 2. And got our radical, or our fraction out of underneath the radical. Got a radical out of the denominator. That would be our simplest form right there. All right, if you look at 9, A and B, obviously it's the same exact problem because once again, we're going to show you 2 different ways to go about doing this. One, just keeping everything in radical form. The other, going with exponential form, just to kind of continue to give you some options to see whatever works best for you guys. And then, you know, going forward, you can, whichever method works for you, you could do that. So if I rewrite this, I'm gonna continue with the strategy of writing as small a base as possible. So I have 6th root of 2 to the 4th, right? So if we're thinking about simplifying this, if I, on the side over here, if I say, if I had 6th root of 2 to the 6th, I think everybody would agree that that's just gonna equal 2, right? So when we're thinking about what we need to multiply this by, we just need to figure out how many more 2's do we need to get to 2 to the 6th. Right, so when we're rationalizing our denominator here, if we multiply by the 6th root of 2 squared, that's adding the 2 more 2's that we need. That's going to get us to the 6th root of 2 to the 6th. So when we simplify this, right, we now have 6th root of 2 squared divided by, this is going to be 6th root of 2 to the 6th. Right, so when I simplify that, the 6th root of 2 squared, it's kind of like a problem from the first page there. So we'd have, if I rewrote that in fraction form, we got 2 to the 2/6 over, this is just going to equal 2. So now this is 2 to the, I can simplify that 2/6 to be a 1/3. So we have the cube root of 2 all over 2. All right, if we wanted to do that in exponential form, if we thought maybe we'd do a little bit better with that, we could rewrite this and I'd still say I got 1 over 6th root of 2 to the 4th like we said. That 2 to the 4th, if I wanted to, 6th root of 2 to the 4th, if I wanted to rewrite that in exponential form, I'd say 1 over 2 to the 4/6, right? So I'm going to simplify that to 1 over 2 to the 2/3. So we got to figure out, in this case, to rationalize our denominator, we need to figure out how to make that exponent an integer with this. So we got the 2/3, so what do we need to multiply by in each case here? We need to multiply by 2 to the 1/3 power. Right? When we do that in our denominator, what we're left with is 2 to the 3/3, because when you multiply, you add. And then when we simplify this, we've got cube root of 2 all over 2 to the 3/3, which is just 2 to the 1st. And we see that we have the same exact answer. Both methods get you to the same place. Neither one is really that much longer or shorter than another one. It's really just what you're more comfortable with dealing with. All right, last one that we're going to do for the day here, and then kind of leave you guys with some practice problems. If we do 9C, we got 18 divided by 4 times the 5th root of 2,187. So if you're looking at your exponent tables that hopefully you created at the start of this, you're probably noticing that 2,187 is not on there. If you take a closer look, though, there is one that's kind of the power that you would see right before that. So if you look at 3 to the 6th, that's 729. So if you multiply that by one more 3, that's going to get you to our 2187. So if we simplify this, we got 18 divided by 4 times the 5th root of, 3 to the 7th power. All right. Let's just kind of on the side here say if we have 5th root of 3 to the 7th, I could rewrite that as the 5th root of 3 to the 5th times 3 squared, right? This value right here, the 5th root of 3 to the 5th, we can take that out and just make it a 3 on the outside. So this is really the same as saying 3 times the 5th root of 3 squared. All right, how does that help me? It makes it a little bit better. So now on the outside, we've got 18 over, this is going to be what? This is going to be 18 over the 4 and 3 are going to multiply together. So we're going to have 18 over 12 times the 5th root of 3 squared. All right, I would say now at this point, you've got a couple things you can do. The 18 and the 12 you can simplify. I think that's probably a good idea. Let's make this a 3 and this a 2. All right, the 5th root of 3 squared. If we just want to leave it as a radical down there and we think about what do we need to do in order to rationalize this, we need to multiply this. How many more 3's do we need so that the radical is out of the denominator? Hopefully everybody can see that we need 3 additional 3's in this case. So we need to multiply by the 5th root of 3 to the 3rd. So we got 5th root of 3 to the 3rd over 5th root of 3 to the 3rd. All right, when we simplify that out, we now have what? We've got 3 times the 5th root of 27 all over, what are we at? We're at 2 times, I'm just going to write it out the long, we got 5 times, or 2 times the 5th root of 3 to the 5th. Right, so if we just take this one step further, we have 3 times the 5th root of 27 still up top, and that's going to be all over 2 times 3. Our 3's can cross out, and this is going to simplify all the way down to the 5th root of 27 over 2. And that would be our simplest form for that. Obviously a little bit more challenging with that. We're going to stop for there with the worksheet for today. In your next lesson, you're going to get into